So this is your third and final mock, which I'm going to run through now. Here's the first question. So it says, Figure 1 shows a volume of hydrogen gas collected when a sample of magnesium reacts with an excess of dilute hydrochloric acid. The rate of this reaction can be studied by measuring the time it takes for a given volume of hydrogen to be collected, and here's the graph of volume of hydrogen against time. And the first question is to state the meaning of the term rate of reaction. So this is the change in concentration of product per unit time, in this case seconds. And state and explain what has happened to the rate of this reaction at point W. So point W is here, you can see it's flattening out, and what that means is that the reaction is stopping because the reactants have run out. So there you can notice there are 2 marks for this question. So you'd say reactant or limiting reactant has run out, because it doesn't mean that both reactants have run out, it's the one that is, well, if one of them has run out, then it's the reaction will stop. So limiting reactant has been used up. Therefore, reaction has stopped. So here we've got, in terms of collision theory, explain why at a fixed temperature the rate of this reaction doubles when the concentration of the hydrochloric acid doubles. So this question kind of came up in the second piece of coursework if you did that. And the answer is that the number of reactant particles doubles, or reactant particles in a given space doubles, therefore the frequency of collisions doubles. And then in the study of the reaction in part A, a student referred to the activation energy. State the meaning of the term activation energy. This is one of the definitions you need to know. It's the minimum, and that's the important word, the minimum amount of energy a particle must have to react. And then complete figure 2 by drawing the shape of the reaction profile from reactants to products for an exothermic reaction. Show the position of the products, show and label the activation energy. So for an exothermic reaction, that means that energy is being given out, and so the energy of the products is lower than the energy of the reactants, because the difference in those energies is the energy that was given out. So the products will be down here somewhere, as long as they're lower than the reactants, that's fine. I need to label it products. And then the reaction profile will go up first and then back down again, because this peak here is the activation energy. So it's the energy that is needed to be put in before the reaction will happen. So you put in that energy and then the reaction happens and the products are formed. So the barium metal reacts very quickly with dilute hydrochloric acid, but reacts more slowly with water. Write an equation for reaction of barium with water. So it's not with steam, so barium oxide is not made. With water, it's barium hydroxide. I think this came up in your last mock actually. So hopefully you've revised, or you did revise, what barium hydroxide was. So remember, it's 2 OHs for the Ba, and hydrogen as well is formed. And then to balance that, you need 2 waters. And then a solution containing barium ions can be used to show the presence of sulfate ions in an aqueous solution of sodium sulfate. Write the simplest ionic equation for reaction that occurs at the table as observed. So basically the barium ions are combining with the sulfate ions to make barium sulfate, which is a white precipitate. So you have Ba2+, and remember that sulfate ions are SO4 2-, and that goes to make BaSO4, and the observation would be a white precipitate, which you can abbreviate to PPT. And then state 1 use of barium sulfate in medicine. Explain why this use is possible given that solution containing barium ions are poisonous. Again, a question that came up in the last mock. So the use is a barium meal. And the explanation is that barium sulfate is insoluble. And you've got to state that barium sulfate is insoluble. Don't say it is insoluble or barium is insoluble. It's the barium sulfate that is insoluble. So you must make sure you state that it's that compound. So this next question of the definition for you: a study of equilibrium is important for studying chemical reactions. State Le Chatelier's principle. So it states that any reaction at equilibrium will shift in the direction that opposes any change made to it. Or something of that ilk. The important points here are to say the reaction at equilibrium, saying that will shift in direction, and saying this opposing. And this is the case where you can say this general change. When you start talking about specific changes, and you have to make point out those specific changes. This next question demonstrates very clearly the two different answers you need to put for catalysts. It's quite nice to put it this way, because hopefully you'll then recognise the two different answers. So it says catalysts play an important role in many reactions. State the meaning of the term catalyst and explain general terms how catalysts work. So the meaning of the term catalyst is what it does, and it speeds up the rate of reaction without being used up. If you say without being chemically changed, you must say that it hasn't been chemically changed at the end of the reaction, because remember, it does get chemically changed during the reaction, it's just it gets changed back again to its original state at the end. So it's easier to say without being used up. And then how catalysts work is the whole idea that it gives an alternative route that has a lower activation energy. So gives the reaction alternative route, or an alternative reaction pathway, you could say, with a lower activation energy. Next, state the effect, if any, of a catalyst on the time taken to reach equilibrium. This decreases the time taken. It's a kind of strange question they've asked there. It hasn't said the rate. The time taken to reach equilibrium will be faster, but in terms of the number for the time, it will be lower. So it will decrease the time taken to reach equilibrium. And state the effect, if any, of a catalyst on the position of equilibrium. This has no effect. Remember, a catalyst just increases the rate of reaction. It will not shift the equilibrium in any direction. So this is a slightly different way of asking Le Chatelier principle questions. It's not asking you to actually explain your answer, it's just asking you to pick the correct reaction for the question. So you've got 5 reactions here, all with different enthalpy changes, all with different numbers of moles of reactants and products. And it says to choose one of these letters and to answer each of the questions. So the first question, it says, a decrease in temperature at constant pressure shifts the equilibrium from right to left. So if a decrease in temperature is shifting it from right to left, that means the left-hand side must be giving out heat, making it hotter, and therefore must be exothermic. So the right-hand side must be endothermic. Remember, these numbers are all for the forward reaction, i.e. going to the right, and so the only one that is endothermic is this one here, plus 58. Remember, a positive enthalpy change means it's endothermic. So this first one is R. Then it says the next one, this equilibrium uses concentrated phosphoric acid as a catalyst in a hydration reaction. So you need to look at which one is a hydration reaction. This is kind of an alcohols question, really. Remember, concentrated phosphoric acid is used in the hydration of ethene to make ethanol, which is this last reaction, T. And then we've got a decrease in pressure at constant temperature shifts the position of the equilibrium from left to right. So we're going from left to right. a decrease in pressure goes from left to right. So the right-hand side must take up more space because decreasing pressure gives it more space. So there's going to be more moles on the right than the left. So we're going to look up at our letters, and which one has more moles on the right and left. This one has 2 on both sides. This one has 4 and 2. This one has 2 and 1. This one has 2 and 4. This one has 1 and 2. So this one here has 2 on the right and 1 on the left. So it's R again. And then there is no change in the position of the equilibrium when the pressure is increased at constant temperature. So no change. That means that there must be the same number of moles on both sides. So this one has 1 and 2, this one has 2 and 4, 2 and 1, 2 and 4, and this one has 2 moles on the left hand side and 2 moles on the right. So P is the answer to the next question. And finally, the last one, an increase in the concentration of steam at constant temperature and constant pressure shifts the equilibrium from right to left. So adding steam shifts it from right to left. So that means if we're adding steam, increasing the concentration of steam, means that steam must be on the right for the equilibrium to want to shift to the left to get rid of it. So which reaction has steam on the right? Q has steam on the right. See? Oh, H2OG. H2O gas. So Q is the answer to our last one. Now, this next question says it's about the extraction of metals, but actually, as you can see, it's starting with a Hess's law question. So, as manganese can be extracted from Mn2O3 by reduction with carbon monoxide at high temperature, use a standard enthalpy of formation data from the table and the equation for the extraction of manganese to calculate the value of the standard enthalpy change of the extraction. So you can see that actually this is the 3rd time in a row that formation enthalpies have been in the table, which suggests that maybe the next one would be combustion enthalpies, or maybe bond enthalpies. I would be surprised if they use formation enthalpies again. And the fact of using formation enthalpies means that we are going up first with our arrows. So we're going to draw all arrows up first, and then put the numbers on. So the number for manganese oxide is minus 971, so minus 971 on the first one, and then you got 3 times minus 111 for the carbon monoxide, so we got minus 333, and then 2 manganese, well that's already an element, so by definition that has a enthalpy change of formation enthalpy of 0, and then minus 394 times 3 for carbon dioxide is minus 1182. We are then swapping over the first 2 arrows so that we go down first and then back up again. These 2 become positives, and then we add them all together. So we've got plus 971, plus 333, minus 1182, and that gives us an answer of plus 122 kilojoules per mole, but you never need to put those units in to get the marks. Then it says state why the value of that standard enthalpy formation of manganese is 0, and that is by definition. The next question, so this is a metal extraction question here. Titanium is extracted in industry from titanium oxide in a 2-stage process. Write an equation for the first stage of its extraction, which titanium oxide is converted into titanium chloride. So this is just a standard equation that you need to learn. So it's titanium oxide plus chlorine plus carbon, and that goes to make your titanium chloride, which is TiCl4, plus either carbon monoxide or carbon dioxide. I'm going to do carbon dioxide because there's no need to balance the carbons, and we just need 2 chlorines in order to balance the whole equation. And then write an equation for the second stage of the extraction in which titanium 4 chloride is converted into titanium. So you've got titanium chloride, and then either sodium or magnesium. I'm going to choose magnesium because it's the one that generally people get wrong, because remember magnesium chloride is MgCl2, whereas sodium chloride is just NaCl, and we'll need 2 magnesium chlorides and 2 magnesiums in order to balance. If you chose sodium, it would be 4 sodium chlorides and 4 sodiums in order to balance it. So next is your obligatory balancing question. You should get 4, 8, 7, 8. That's a pretty tricky one to balance that one. And remember, whenever you get a balancing question, leave it and come back to us. Just remember to come back to us, unless you can get it straight away. In the final stage, chromium is extracted from Cr2O3 by reduction with aluminium. Write an equation for this reaction. So you got chromium oxide plus aluminium. This isn't the one you learn, but you should know that aluminium oxide is Al2O3, and you'll make your chromium. The oxygen's already balanced. You're just going to make 2 chromiums, and you need 2 aluminiums in order to do that. Here's another Hess's law question. Shows you a cycle, which we've actually done before in lesson, where we worked out this value by dissolving anhydrous copper sulfate and hydrated copper sulfate, worked out the delta H values for those and swapped this last one. So state Hess's law. Firstly, so Hess's law states that that the enthalpy change for a reaction is independent of the route taken from reactants to products. And then write a mathematical expression to show how delta H exp, delta H1 and delta H2 are related to each other. So the arrow that we're going to have to swap round is this one to work out this delta H exp. So this will go the opposite direction, so we'll have delta H2 but negative delta H2. So your delta H exp is going to be delta H1 take away delta H2. So delta H exp equals delta H1 take away delta H2. And then it says, use a mathematical expression that you've written in part B and the data book values for the 2 enthalpy changes, delta H1 delta to calculate a value. So you've just got to put these numbers into that expression. So you're going to get minus 156 minus 12, which equals minus 168 kilojoules per mole. So we've got another energetics question. This requires you to use Q equals mt delta T. So the student added 0.0210 moles of pure anhydrous copper sulfate to 25 centimeters cubed, deionized water in an open pulsary cup. An exothermic reaction occurred and the temperature of the water increased by 14 degrees. Use these data to calculate the enthalpy change in kilojoules per mole for the reaction of copper 2 sulfate. This is the student value for delta H1. In this experiment, you should assume that all the heat released is used to raise temperature for 25 grams of water. So first mark is for Q equals mc delta T. Then you've just got to put the numbers in. So remember, you're heating the water, so it's the mass of the water that must go in here. So that's 25 times your specific heat capacity of water, which is 4.18. That's given to you. And then times your temperature change, and it tells you it's increased by 14. So you times it by 14, and that equals 1,463. This is in joules. If you put that into kilojoules, divide by 1,000, so it's going to be 1.463 kilojoules. Remember, an enthalpy change is measured in kilojoules per mole, so we've got to divide this number by the number of moles that gave out that much heat energy, and that's given to you here. There's no need to work out the number of moles from a mass or an MR or anything. It's told you how many moles already, so you just need to divide 1.463 by a number of moles, 0.0210, and that gives us 69.7. Then the last thing to do is to work out whether it's going to be negative or positive. You can see that the temperature increased by 14 degrees, so it's an exothermic reaction, so it's negative 69.7 kilojoules per mole. Then it says, suggest one reason why the student value for delta H1 is calculated in part D1 is less accurate than the databook value given in part C, and that will be due to heat loss. So value, or sorry, you could say that there was more heat lost. And then finally, we've got suggest one reason why the delta H exp cannot be measured directly. There are two more obvious answers to this. Firstly, it's very difficult to, something you could say is very difficult to add the exact amount of water that is added during the reaction. Very difficult to add exact amount of water to turn it from anhydrous copper sulfate into hydrated copper sulfate. The other thing is that both anhydrous and hydrated copper sulfate are solids, and it's very difficult to measure the temperature change of a solid, and so that will be the other reason. Glucose is an organic molecule. Glucose can exist in different forms in aqueous solution. Here's glucose. Deduce the empirical formula of glucose. Now, I don't know why they've asked this question. It's a Chem 1 question, really. It's a bit of a waste of a mark, I think, in terms of where they're concerned. But anyway, so there are 6 carbons, 1, 2, 3, 4, 5, 6. 6 oxygens, 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So the molecular formula is C6H12O6. So the empirical formula would be CH2O, because all those numbers can be divided by 6. Never, ever leave 2 formulae though. Make sure you cross out the one that is a molecular formula to leave the empirical formula. Only ever write one formula. Next question is an infrared spectrum question. So it says, state why it is possible to suggest that in the solid state very few molecules have the structure shown. So the structure, you can see, has OH peaks, or groups, alkyl OHs, and a seal bond O. If we look at the infrared spectrum, you can see there is a peak at around 3,300 where you would expect an alkyl OH peak. Now, I have said to you before that it should be a rounded peak, but this one doesn't seem to be. The reason why that isn't the answer is because a seal bond O peak should occur at around 1,700, and that is missing. You can see that. So you can say that the seal bond O peak at 1,700 centimeters to the -1, which is what wave numbers is measured in, is missing. In the absence of oxygen, an aqueous solution of glucose can be fermented to produce ethanol for use in alcoholic drinks. Write an equation for this fermentation reaction and give 2 other essential conditions for the production of ethanol in this fermentation. So you got given the glucose formula earlier, so C6H12O6, and that forms ethanol, C2H5OH, and carbon dioxide. And to balance this, you need 2 carbon dioxides and 2 ethanols. The first condition is yeast. You need a yeast catalyst in order for this to work, and you also need a temperature of around 37 degrees. Remember, I always say just remember body temperature, because that's where our enzymes work best, 37 degrees Celsius. And then any ethanol present in the breath of a drink can be detected by using a breathalyzer. The ethanol is converted into ethanoic acid. The breathalyzer has negative and positive electrodes. A current is measured and displayed in terms of alcohol content. The overall redox reaction is as follows. There it is. Draw the displayed formula for ethanoic acid. So you should know that is C, double bond O, and then because it's a displayed formula, the OH must have all the bonds shown like so, and this is CH3 first. Deduce a half equation for the reduction of atmospheric oxygen to water in acidic solution at 1 electrode of the breathalyzer. So we've got oxygen turning into water, and we can just balance this redox half equation as we always do. So first balance anything that's not hydrogen or oxygen. They're both hydrogen or oxygen, so we can't do that. Then balance the oxygens with water. We're just going to double this water up, like so. Then balance hydrogens with H+, so we need to add 4 H+ onto the left-hand side, and then balance with electrons, so we also need 4 electrons. And then deduce a half equation of the oxidation of ethanol in water to ethanoic acid at the other electrode of the breathalyzer. So we've got CH3, CH2OH turning into CH3, COOH. Balance anything that's not hydrogen or oxygen. Carbon, 1, 2, 1, 2 is already balanced. Then balance oxygens with water. So we've got 1 on this side and 2 on this side. So we're going to have to add 1 water onto this side. Then balance your hydrogens with H+, so you've got 1, 2, 3, 4, 5, 6, 7, 8 on this side, and 1, 2, 3, 4 on this side. So we need another 4H+ on this side, and therefore another 4 electrons to balance the charges to make them both 0 in this case. And then the earliest breathalyzers were laboratory chemicals to oxidize the ethanol to ethanoic acid. Detection was by colour change. Identify reagents or combination reagents that you would use in the laboratory to oxidize ethanol to ethanoic acid. Say the colour change, so we're oxidizing, so we need acidified potassium dichromate, and you will see a colour change of orange to green. And then the fermentation of glucose from crops is the main method for the production of ethanol. The product is called bioethanol, and it has been declared carbon neutral. What is carbon neutral? Again, this is in your last mock, and that is that there is no net or overall, one or the other, addition of carbon, and you must say to the atmosphere for the mark. So it's very specific what they want there. And then, other than carbon neutrality, set the main advantage of the use of glucose from crops as the raw material for the production of ethanol. And that is the idea that the crops are renewable. So this is a renewable process or a sustainable process. And then give one disadvantage of the use of crops for the production of ethanol. So you can have one of a number of things here. Two things are that land isn't being used for food, so could create a food shortage. And second, CO2 may be made during harvest or transportation, or any named process that would create CO2 during the production of, or the production of the crop to make the ethanol. And that's very similar to an answer you had to put in a previous mock. So next question says hydrazine N2H4 decomposes in an exothermic reaction. Hydrazine also reacts exothermically with hydrogen peroxide when used as rocket fuel. Write an equation for the decomposition of hydrogen into ammonia and nitrogen only. So you've been given what hydrazine is, it's N2H4. And you should know what ammonia is, it's NH3. Because you need to know that what ammonia is for one of the nucleophilic substitution mechanisms. And you're making nitrogen as well, which is N2, goes on in pairs. And then to balance that, you will need 3 hydrazines and 4 ammonias. And state the meaning of the term mean bond enthalpy. So this is the average amount of energy, amount of energy needed to break 1 mole of a certain covalent bond, and that's what a lot of you are missing out in your answer, and that could be my fault, to be honest. So it needs to be a covalent bond, and there's the other part that gets the mark, taken over a range of different compounds. Then if we move down, we've got another Hess law question, actually, and so here we've been given some mean bond enthalpies, there they are, and we need to use this data to calculate the enthalpy change for the gas phase reaction between hydrazine and hydrogen peroxide. So there it is. So with mean bond enthalpies, your arrows will go down first. So you're going to draw arrows from all your molecules going down, and then you're going to draw on your arrows exactly what calculation you're doing. So here you've got 1, 2, 3, 4 NH bonds, which all have monoenthalpies of 388. So you're going to have 4 times 388 plus the 1 NN bond, which is 163, because it's just a single bond between those two, and that gives you 1715. And then on the next one, hydrogen peroxide, you've got 1, 2 OH bonds per molecule, but there's 2 molecules, so that's going to be 4 times OH, so that's 463. So 4 times 463 plus 2 times this OO bond, which is here, 2 times 146. And that gives us 2,144. You then got one NN triple bond, which has a bond enthalpy of 944, and then you got 1, 2 OH bonds, but times that by 4 because there's 4 water molecules, so 8 times 463, which equals 3704. So it's these big numbers that we're using in our calculation, but these last 2 arrows need to be swapped round because we need to go down first and then back up again. So these 2 arrows are going to get swapped round, and these 2 numbers are going to be made negative instead. So it's minus 944 and minus 3704, and then just add them all together. So you got 1715 plus 2144 minus 944 minus 3704, and that should equal minus 789. This is the sort of question where it's very, very easy to get some of the numbers wrong or to type things into your calculator incorrectly. So this is definitely a question where you should be checking your answer more than once. So when you finish the paper, come back to it, just make sure your numbers still add up to the numbers that you thought they were in the first place. Next question, the refrigerant R410A used in air conditioners is a mixture of 2 fluoroalkanes, pentafluoroethane and difluoromethane. The mechanism for the reaction of fluorine with either an alkane or fluoroalkane is similar to that for the reaction of chlorine with methane. Name the type of mechanism for the reaction of chlorine with methane. So this is free radical substitution, not chain mechanism. Has to be free radical substitution. You do not get the mark if you put chain mechanism. And then it wants you to draw out the mechanism. So, initiation step, it's with fluorine. So you got F2 goes to make 2 F dots. Remember that bond between the 2 F's and the F2 is being broken. And so you make 2 atoms by themselves, but they are free radicals. They have unpaired electrons because the pair of electrons in this bond, one of the electrons has gone to each fluorine atom. First propagation step, where you got the F dot reacting with, it says you're reacting with CH3F. And remember, the first thing the free radical does is it grabs an H. So you're going to make HF, and then whatever's left over, CH2F, and that's going to be a free radical. Remember, your atoms, in any equation where you've got an arrow, your atoms need to balance and your charges need to balance. So you've got 1, 2 F's on this side, 1, 2 on this side, and 1, 2, 3 H's on this side, and 1, 2, 3 H's on this side. You should always have them balancing. Just because it's a free radical in there, it doesn't matter. Still, we need to balance the atoms, which some of you weren't. And then you've got the CH2F dot reacting with an F2, and that makes your product CH2F2, and it makes F dot again to go back into the first propagation step. So those 2 go over and over again. And the termination step needs to make 1, 2 difluoroethane. That's going to react together 2 CH2F dots to make CH2F, CH2F. Now you've only got the mark if you drew this out structurally, and the reason for that is because it gave you a name to work to. If you wrote C2H4F2, then that could be 1,1 difluoroethane. So if there is any ambiguity in the molecule that you draw, and that it might not be the molecule they're asking for, then make sure you draw it out structurally instead. And then write an overall equation for the reaction of fluorine with ethane to form pentafluoroethane by this mechanism. So ethane is C2H6, and you're adding fluorine, and you're making CF3CHF2, so you're putting 5 fluorines in there. And remember, you make HF. Remember, in this first propagation step, you're making HF. A lot of people were putting H2 here, but remember, it's the hydrogen halide that is made in the first propagation step, and to balance this, you need 5 HFs and 5 F2s. So the refrigerant R112A, which is that, has been banned because of concerns about ozone depletion. Give the IUPAC name. So this is going to be, you've got 4 chlorines, and the the chloro is going to come before the fluoro because it goes in alphabetical order. So you've got 1, 1, 1, 2, and for 4 it's tetra. So it's a tetrachloro, and then both the fluorines on the second carbon, so 2,2-difluoro, and it's FLUO. If you spell that wrong, you should lose the mark, and then ethane on the end because it's just 2 carbons in a row. Right, the overall equation for the decomposition, so it says here, nitrogen monoxide catalyses the decomposition of ozone to oxygen. So you have to write the overall equation for the decomposition, so that's just 2O3 goes to make 3O2. No need for the NO in there. If you're going to put it on, then it's going to be on the arrow because it's a catalyst. It doesn't get used up during the reaction, so you don't want to have a reactant or a product. If you put it on both sides, there's no point because it's like putting, if you put anything on both sides, it doesn't make any difference. So you don't want anything on either side. That is the only thing that will get you the mark by putting NO on the arrow if you want to put NO in there. But if the NO wasn't there, you'd still get the mark. It's just 2O3 goes to make 3O2. And then you've got to use the overall equation to do step 3 in the following mechanism that shows how nitrogen monoxide catalyses the decomposition. This is quite a tricky question actually, and what you've just got to make sure you do is make sure that these, the 3 steps add up to make 2O3 goes to make 3O2. Now in these 2 steps you've already got the 2O3 and you've got the 3, you've only got 2O2, so you're going to have 1 O2 on the right hand side of the arrow. You've already got your O3s, but then you've got to make sure that anything that's not O3 or O2 cancels. So you can see the O doesn't cancel yet because the O is on this side, but there's nothing on this side at the moment. So you need O on this side, and then NO doesn't cancel either because you've got no NO on this side and you've got no NO on this side. So you need to have NO on this side, not on this side, sorry. You have to have NO on this side so it cancels out throughout. And then you've got NO2 on the right hand side, but no NO2 on the left hand side yet. So you need NO2 plus O goes to make O2 plus NO. And if you added all those 3 steps together now, you could cancel out the NO2s, the O's and the NOs, and you'd end up with 2O3 plus goes to 3O2. That was a very tricky question, and I'll be very impressed if you got that. Now we come on to our mechanisms questions. So we've got to consider these following reactions. It says name out allying mechanism for reaction 1. So reaction 1, you've got an alkene with HBr going on to make bromoalkane. So that is going to be electrophilic addition. So that is our mechanism. Just got to learn these names. Some of you mixing up electrophilic with nucleophilic. So electrophilic addition. And the mechanism, you've got your alkene that you start with, HBr underneath. So your first arrow comes from the double bond to the H, and then from the HBr to the Br. Make sure you draw your mechanisms big, because otherwise it's very likely that you're going to not leave yourself enough space to put the arrows in the positions you want them. And then you're going to break that double bond. You're going to have 3 C's in a row. Your H could either go on this C or this C. It's going to go on this C because this one would be a more stable carbocation, because that would perform a secondary carbocation compared to a primary carbocation, which it would be if the positive charge on this one. And a secondary carbocation is more stable because it has a stronger positive inductive effect from the carbons either side of it. So this is your intermediate, secondary carbocation, and then you've got your Br minus left over, lone pair comes in and joins onto your intermediate like that. So make sure you've got your lone pair there, and that will give you 5 marks. And the next one says, name and outline mechanism for reaction 2. So reaction 2 was your 2-bromopropane reacting with ammonia. So this is your more difficult nucleophilic substitution mechanism. So this is nucleophilic, make sure you spell it right, substitution. So you've got a lone pair NH3. NH3 is not charged, and that will come in, attack your C, and then your CBr bond will break and go to the Br, and that will form an intermediate. So you've got 3 C's in a row, and you've got your N with 3 H's on it. Just fill everything in. And then the N has a positive charge, because here it's given away electrons. It was happy here, it had no charge on it, but now it's given away electrons, so it's going to be positively charged. And to get back a neutral charge, it needs to grab some electrons from a bond here. So the H leaves and is actually picked up by another NH3, but there's no need to draw that in. And the electrons in that NH bond quench that positive charge, and that will get you 5 marks. Next question, state a type of reaction in reaction 3. So this is polymerization. And you're polymerizing propene, so your polymer is called polypropene. A lot of people not getting that, and probably one of the easiest questions in the exam. Perhaps you're just used to the harder ones. And then a final mechanism question. The haloalkane produced in reaction 1 can be converted back into propene in an elimination reaction using ethanolic potassium hydroxide. So you've got to just write a mechanism for that. So you've got your bromoalkane, got your OH minus. Remember, it's not KOH is going in there, it's OH minus. That OH minus grabs an H, the H bond breaks, it makes a double bond between the C's, and the Br leaves, and that forms your double bond again. That's all that's needed, no need to draw the product. And then, this is quite a long question on halogens, 5 marks, but you can break it down to the 5 different points. So it says, concentrated sulfuric acid reacts with solid potassium iodide as shown in the equation. There it is. Give 2 observations you would make when this reaction occurs. Now, some of you were writing about yellow solid because of the sulfur and things like that, but you just have to write observations based on this equation. And the only 2 things you're going to be able to see from this equation is the H2, or observe, H2S, and the I2, sorry. So H2S will give you a bad egg smell. You won't be able to see it, but you'll be able to sense it. And the I2 will be a black solid. So those are the only things that you'll get credit for. The sulfur that you might see during this reaction, you won't, because it's not in this equation. And then in terms of reactions, what happens to the iodide ions as reaction? Well, these go from I minus to I2, from a -1 oxidation state to a 0 oxidation state. So they lose electrons. So I minus lose electrons. And then in terms of, I've done that one. State the change in oxidation state of sulfur that occurs during the formation of H2S. So we're going from H2SO4, where the sulfur is +6, and then H2S, where sulfur is -2. So +6 because the 4 oxygens are -2 each, that's -8. The H2 is +1 each, that's +2. To make this equal 0 overall, the S must be +6. And for the H2S, we've got +2 for the 2 H's, and therefore -2 for the S to equal 0. So this is a change of -8. Then finally, deduce the half equation for the conversion of H2SO4 into H2S. So we're converting H2SO4 into H2S. First balance anything that's not hydrogen or oxygen, sulfur's already balanced, then balance oxygens with water, so we need 4 waters on this side, then balance hydrogens with H+, so we've got 8 here, plus 2 here is 10, we've already got 2 here, so we need another 8 on this side, so it's 8 H+, and then we need 8 electrons to balance the charge. It's not automatically the same number of electrons as H+, it's just because this side is 0, and with 8 H+ on this side, has an 8+ charge. So we need 8 negative electrons to balance out the H+ charge to make it 0 overall on both sides. And then final lot of questions. Chlorine is a powerful oxidizing agent. Write the simplest ionic equation for reaction in chlorine aqueous potassium bromide. Now I'm going to do a new video on ionic equations at some point. It should be up by perhaps the Monday of half term. But ionic equations just show you the ions that are reacting. Now chlorine with aqueous potassium bromide is KBr plus Cl2 goes to make KCl plus Br2. But these are all in aqueous conditions, so the KBr and the KCl are going to be floating around in solution as separate ions. So you'll notice that the K will be on both sides, so that won't be drawn. That will just be a spectator ion. And so what we get is Br minus plus Cl2 goes to Cl minus plus Br2, and obviously balance with 2's in front of the Brs and the Cls. So we've got 2 Br minus plus Cl2 goes to make 2 Cl minus plus Br2. And what is observed, you get an orange solution formed from the Br2. And then write an equation for the reaction in chlorine and coal dilute aqueous sodium hydroxide. So a few of you have forgotten or just not revised this. So Cl2 plus NaOH, and then we'll make NaCl plus NaOCl plus H2O. And to balance this, we need 2 NaOHs. So it says give a major use for the solution that's formed by this reaction. So this is used as bleach. And then the name of this is sodium for the Na, and then OCl is chlorate. And then write an equation for the equilibrium reaction that occurs when chlorine gas reacts with cold water. So the fact it told you it was an equilibrium reaction in the question means that you must have an equilibrium arrow in the middle. So you've got chlorine gas reacting with H2O. You're going to make HCl plus HOCl, HOCl, something we like to call it. And then give one reason why chlorine is used for treatment of drinking water even though the gas is very toxic. Now, some of you didn't read that second part of the question and just answered why it was used in drinking water, because it kills bacteria, but that's not the reason it's used even though the gas is very toxic, so you weren't answering the question. The reason why it can be used, which is what it should have said really, why it can be used for treatment of drinking water even though the gas is very toxic, is because it is used in very dilute quantities. And then final question, state how you could test a sample of water that contains chloride ions. In your answer, give a reagent, one observation, that's the Limit equation for reaction. So, to test for halide ions, silver nitrate. Even better if you write acidified before that. That covers all your bases, but actually didn't need that for this mark this time. For chloride ions, that produces a white precipitate, which you know will dissolve in dilute ammonia, if it asks you for a question for that. And then the simplest sign equations are silver ions reacting with the chloride ions to make your silver chloride precipitate. That's it. The nitrate ions don't need drawing because they'd be spectator ions, and, well, they only say chloride ions in the question anyway, so there's nothing to write with that. Please email me if any of the questions I've been through do not make any sense, and I will email back with a prompt response.